Hey everyone, Ronak this side. I hope you all are doing well. So let's say the problem of the day. So the problem here we are given is basically again we are given the edges in form of in form of sub arrays like 1 and 2 is edge, 1 and 3 is edge. So if we have to construct from this similar to tomorrow, what will it take? 1 and 2 had a edge, 1 and 3 had a edge, 3 and 4 also had a edge, 3 and 5 also had edge. So this is basically tree. And we have to return what we have to return. We have to return an array answer. Okay, we have to return an array answer that gonna contain the valid assignment for query I. Okay, so what we are given also a query, and query represent node 1 to 4. So basically here if query is 1 to 4, so we have to travel from 1 to 4. Okay, here 3 to 4, so we have to travel to 3 to 4. Here 2 to 5, so we have to travel to 2 to 5. Okay, and what do we mean by travel? For query, determine the number of ways to assign the weights to the edge in part such that the cost of path between both two given nodes is odd. So basically we have to first find the path and we have to calculate the number of ways to, so that if we find the number of edges, so if we find number of edges, so what we have to do, we have to 2 to the power number of edges minus 1, because 2 to the power is 2 to the power number of edges is number of ways to define the define assign the weights to the edges, and we are subtracting one, basically dividing it by 2, so that we can get only odd number of sums by defining the edges. Okay, similar to what we did tomorrow. So but if we in question it is given that the size of query can be 2 to the power 5. There can be 10 to the power 5 query, and each query and size of number of edges can be 10 to the power 5. So okay, so each query gonna require 10 to the power 5, so it's gonna lead to 10 to the power 10, that going to at the end going to be time limit exceed. Okay, so that are going to give time limit exceed error. So what we are basically going to do here is, for example, we are given entry. Let's consider A, B, C, D, E, F, G. Okay, we are given the tree here, and what we have to calculate is here. For example, here we have to calculate from E to D. Okay, number of ways to assign weight to E to D. So I mean, we know we are going to do it by 2 to the power number of edges from E to D. So how we gonna calculate the number of edge from E to D? Okay, E to D. So the first way is to by doing DFS, considering E as a parent. We are going to do DFS that are at the end gonna require this much space. The go of n, that is total number of nodes. So how we are going to reduce the time? Okay, so basically if we see, if we want to calculate the I mean E to D, what we can do, we can calculate first depth of E. Okay, depth of E. What is depth of E? So 1 2 3, and depth of D, depth of D equal to 1 2. And what is the depth of lowest common ancestor? So first let's understand what is lowest common ancestor. Okay, so ancestor means the previous node or parent nodes. Okay, and common means the common parent node. So D here is a, what is common between D and E? Okay, so common between D and E, which parents are common? So A is a common parent to D and E. Ancestor, not a parent. Maybe grand for D it's grandparent, and for E it's grandparent. Okay, okay, and B is also common for both. Okay, so what we are going to do, we have to find the lowest, closest possible. Okay, so who is closest to both? So of course B is closest. And what is the depth of, so LC here equal to B. Okay, here lowest common ancestor of E and D is B, okay, because B is common, B is ancestor to both, and B is lowest to both, okay. So nothing lower than B can be common and ancestor both, okay. So what is the depth of lowest common ancestor? That is 1. So what we are going to do is number of edges, okay, number of edges between any number u and v, and any two nodes u and v, that gonna become depth of u, depth of u minus depth of v, I mean depth of u plus depth of v minus 2 times depth of LCA, okay. So how we got to this formula? Okay, so for example we have to calculate this, I mean, so this is the depth of E, this is the depth of D. So what is the distance between D and E? Okay, so this is gonna become this, this, and this, okay. So what we have to remove? We have to remove the green part. And what is green part? Green part is basically twice of depth of lowest common ancestor, okay. So depth lowest common ancestor is B, depth of B is 1, and twice of B is 2, okay. So if we apply the formula here, so edges between, number of edges between E and D, E and D is depth of E equal to 3 plus depth of D equal to 2 minus 2 times of depth of lowest common ancestor, that is 1, okay. So it's gonna become 5 minus 2, that is 3. So if you see number of edges is here 1, 2, 3, okay. So 3 is the distance between E to D. So first of all, we are, while we have to, at first what we are going to do is we are going to do DFS on tree where node, parent, and current depth, okay. We are going to do DFS on this tree, and we are going to first initialize an array of we we are going to initialize an array of df depth, called it depth vector, and depth, and that gonna contain, that is of number of nodes, number of node plus 1. We are doing plus 1 because here node is starting from 1, and we are doing plus 1 to exclude the 0. So we are going to do DFS and going to store the depth of each node in first iteration, so we can directly calculate the depth, okay. So what is the code of DFS? DFS of code, so current depth equal to, I mean it's current depth, so depth of current node gonna equal, depth of current node gonna equal current depth. After that, what we're going to do is for a child on our node, adjacent of node, if child is not equal to parent, we are going to do DFS on that, where current node is gonna become child and parent gonna become current node, and do current depth plus 1, current depth plus 1, okay. So this is the whole code to DFS. And about the adjacent, we can also do the adjacent while we did earlier, okay. So for adjacent we can write loop similar we wrote earlier is for core inquiries int u equal to q0 int v equal to q1 adjacent of u dot pushback v adjacent of v dot pushback u. Okay, like that. So here the code of adjacent and how we are going to create the adjacent and how we are going to store the depth of each node. Okay, so if we run this, we can see, first let's create the adjacent for these three. Okay, so here A gonna store B and F. Okay, so if we want to create the adjacent, we here A gonna store B and F, B gonna store C and D, F gonna store A and G, B gonna C, D and A, and C gonna store B and E, E gonna store C, D gonna store B. We got A, B, C, D, E, F. Okay, so this is the adjacent. So we just wrap it in our selection frame. So after we got this, we can simply do the DFS here and create the depth array. So if we create the depth array for node A, B, C, D, for example, here A, B, C, D represents 1, 2, 3. Okay, A represents 1, B represents 2, A equal to 1, 2, 3, 4, 5, 6. I just used, numericals to, alphabet to understand better and don't get confused with numericals here. So DFS on depth, if we create the depth array, this is 0 index, first, second, third, fourth, fifth, sixth. Okay, number of nodes plus 1. And for if we call DFS on, first DFS gonna call in, we are going to start DFS, going to call 1 and current equal to 0, considering 1 as parent, so we are going to call it A. So A gonna do through B and F. Okay, so B is, I mean just write A and B, A and A. Okay, so current node is and parents both gonna become 1. So depth of current equal to current, so depth of A equal to A. Okay, so depth of A equal to 0, and for every child on A we gonna call it for now. So DFS gonna call for basically DFS of A comma 0. We called for A, now you have B, so DFS for B whose parent is A and depth is become 1. DFS for F whose parent is A and okay, node gonna become parent and current increase the depth by 1. Okay, so for B A1 we have to first store the depth of B, so depth of B equal to 1, depth of F that is 6 equal to 1, and for B we are going to call C, D and A. Okay, so C, D and A, but A equal to parent, so it doesn't get called, so we are going to call for C and D only. So DFS C whose parent is B and DFS whose parent is on C and D. Okay, D whose parent is B and depth is 2, and for C and D depth is 2, so for C and D depth is 2, so we called for, I mean After that, we are going to call for C. So for C, we are going to call B, but B is parent, so we are going to only have to call for E. Okay. So let's call the E. So for DFS, we from B we called D, I mean from not B, from C we call DFS of E having C as parent and depth equal to C. So depth of E is 3. So E is 3. And now E gonna call DFS on E, every child of E. So that is C. But C is parent, so we're gonna skip it. And now we have to call on DFS of D. So DFS of D is E. Wait, is D connected to E? Hold on. D is B. I wrote B. Okay. So B is parent to D. So we skip it and now come to F. So F, we wanna call F for A and G, but A is parent, so we are going to only call for G. So DFS on G, whose parent is F and depth is 2. Okay. So for DFG, we also have G. Okay. So we got 7 here, G here, whose parent is F, 7. The depth of G is 2. Okay. So depth of G gonna become 2. So that's how we gonna call the depth. And at last, what we are going to do is, I mean, number of number of edges equal to depth of U plus depth of V minus twice of depth of LCA of U and V. Okay. So the number of edges we are going to calculate by using the sum of depth of V plus depth of U and subtracting that by twice of depth of LCA of V and V. And now the main question is how we are going to calculate the LCA of U and V. Okay. So now we have to focus on LCA, calculating the LCA of U and V. Okay. So if we see our tree here, so now how we are going to calculate the lowest common ancestor of any two nodes. So the first approach is, I mean, we are going to calculate. We can calculate this by using a naive approach where we are at E and D and do DFS from E and then again at A to D. So that's gonna and find the LCS. So, but that also gonna inverse is gonna lead to big of n time complexity. So you have to reduce it into log of n. Okay. So how we can reduce it to log of n? So what we are basically do is first we are going to a concept called binary lifting, where we are going to jump in power of 2. Okay, so if we have to reach 19th, we are going to jump like 2 to the power 4, that is 16, 17, 18, 2 to the power 1 and 2 to the power 0. That's gonna lead to 19. Okay, what I'm saying is first of all we are going to create an ancestor vector that contain I mean that gonna contain array of size array of int type of size. For example, I mean we are going to use 18 and size of ancestor gonna become number of nodes, number of nodes plus 1. Okay, so we are excluding 0 here. And so how this gonna help us? So this is going to help us by just, for example, why we used 18 here, because 2 to the power 18 is greater than 10 to the power 5. Okay, so we are going to jump over. So for example, if we created, so number of nodes here is 1 2 3 4 5 6 7. So we have to create an of 8. So for example, we created in this 1 2 3 4 5 6 7 8. Okay, and 18 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 and 18. So this is the, and the 2D gonna, how the, I mean, what the 2D ancestor matrix gonna look like, where each row belongs to an, I mean, each row belongs to a node. It represents A, B, C, D, E, F, G. I mean, primarily 1, 2, 3, 4, 5, 6, 7, and these all gonna represent 2 to the power, I mean, 2 to the power 0, 2 to the power 1, 2 to the power 1, 2 to the power 2. So basically, these all are gonna represent index, that is 0, 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16, 17, and 18 here. Okay. So what we are basically planning to do here is we are going to, I mean, add the every answer. We are going to write the every ancestor of here. Okay. So for example, here what we are going to write is 2 to the power 2 ancestor. I mean fourth ancestor of A. Okay. Here what we are going to write is 2 to the power 6. That is 64th ancestor of. Okay. So and if we have to reach here, I mean 34th ancestor. I mean for example here 64 ancestor is some example X. Okay. For example here it's X, and we have to reach the 65 X ancestor. So if X is not in our scope, so G. So if you want to reach the 65, I mean 65th ancestor, so but the next is 128. Okay, this equivalent to 128 ancestor, this equivalent to 64th ancestor. So what we are going to do to go to 65, we are going to ask G, what is your first ancestor? That is 1. Okay, so this represents 2, this represents 4, this represents 8, this represents 16, this represents 32. So what is the first ancestor of, I mean, G? So for example, it's F. Okay. So the 65th in ancestor of A gonna become 64th ancestor of G, and A, that is G, and first ancestor of G, that is F. Okay. That's how we gonna do. So how we are going to do is fill this table. Okay. So we are going to fill this table while doing the DFS. While doing the DFS, what we can do is to fill this table, we are going to over every node. I mean the code of DFS we wrote here is just, and after every node what we are going to do is def, I mean this part of code just, so what is the first ancestor, I mean 2 to the power 0th ancestor of, so, so in first index gonna represent node, second index gonna represent the ancestor number. So here 0 represent first ancestor because 0 is represent the power. So what is the first ancestor of any node? Okay, so the first ancestor of 3 is 2. Okay, the first ancestor is going to be parent. So the first ancestor of any node going to parent node. And how we are going to do the other ancestor of this node? We are going to do it by just lower it a little bit more. J equal to 1, j less than 18, j plus plus ancestor node of A equal to ancestor ancestor of ancestor of j, that node jth minus 1 ancestor and 2 to the power j minus 1 ancestor work with the so jth minus 1 ancestor this whole is j minus 1. So what I wrote here is, if you look, I wrote here, so first a I wrote there is ancestor of n, jth ancestor of n node is ancestor of this node, which is ancestor of node j minus 1, j minus 1, and then j minus 1. So how this gonna help us to find this? So basically, for example, so here DFS code for DFS. We are going to DFS, do the DFS, and which tree? I think let's consider this tree. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, that's how we are going to do the DFS on this tree. So first let's call 1, 1, 0. 1, 1, and 0. Okay, so after calling 1, 1, and 0, after calling 1, 1, and 0, 1, 1, 0, it's first mark the, let's consider a depth here, which is gonna record the depth of every, this is the depth array for every node. So the depth of first node, A, the depth of A equal to 0 because it's the depth, so depth of A equal to 0, and first ancestor of 1 is 1. Okay, so the first ancestor of 1 is 1. So 0, this is first ancestor of 1 is 1 because the first, second, third, every ancestor of 1 is 1 because 1 is root node. There is no more further ancestor of 1. So the first ancestor of 1 gonna become 1, and we are going to run it till 18. And if we see z for j equal to 2, ancestor of 1, j equal to 1, first ancestor of 1 equal to ancestor of ancestor of second ancestor of 1 equal to ancestor of first ancestor of 1, second ancestor of first ancestor of 1. Okay, first ancestor of first ancestor of 1. Okay, so this is first, what is the first ancestor of 1? So this is 0. First ancestor is 0, so first ancestor is 1 here, so this is gonna return 1, so it's gonna lead to again 1, this also return 1, so it's gonna return 1. And if you run this, all gonna filled with 1. Okay, because there is no more further ancestor. So for any code, if you try run the 16, so it's always gonna return ancestor of first ancestor of 1, 16, 2 to the power 16 ancestor of 1, that's also gonna represent, they are also gonna add the end, gonna return, because any ancestor of is 1, so a of 1, I mean a of 1, 15, and 1. Okay, so what is the 2 to the power 15 ancestor of 1? That is also 1. So a of 1, 0, that also gonna become 1. Okay, so by recursively all gonna become 1 for a because there is no more further ancestor for a. And similarly, if we do for 2, so after completing the for loop, we are going to call DFS from that adjacent list. And where is the adjacent list for this? We can create here the adjacent list. 1 is connected to 2 and 6. 2 is connected to 1 and 3 and 4. 3 is connected to 2 and 5. 4 is connected to 2. 6 is connected to 1 and 7. 7 is connected to 1. 5 is connected to 3. 1, 2, 3, 4, 5, 6, 7. Okay, so this is our adjacent. So after calling 1, we are going to call DFS on 2 and 6. So call DFS on 2. The parent of 2 is 1 and depth of 2 is 1. Call DFS on 6. Parent of 6 is 1 and depth is 1. Okay. So first mark the depth of current node, that is 2 and 6, that is 1. 2 and 6, which is 1. And then ancestor of current node is parent, so parent of 2 and 6 is 1. And now do the run for 2. For 2 we have to mark every ancestor. So if we do, what is the second ancestor of 2? So for 2, first, second, every ancestor gonna become 1. So recursively it also gonna become 1, and similarly for 6 it all gonna filled with 1. This all also gonna filled with 1. Okay, you can dry run it by own, dry run in your own, and you can see. And after that, for 2 it gonna call 1, 3 and 6. We are not going to call 1, it's going to call 3 and 4. 3 whose parent is 2 and depth is 2. 4 whose parent is 2 and depth is 2. So for 3 and 4 depth is 2. For 3 and 4 depth is 2, and parents of 3 and 4 is 2. Okay, so the first ancestor of 3 and 4 is 2. The second ancestor gonna become 1. How the second ancestor gonna become 1? Because if we find the second ancestor a of second ancestor of 2, wait, second ancestor of 3. Okay, for ancestor of 3, and which second, 2 to the power 1 ancestor of 3, so that gonna be ancestor of first ancestor of 3 and 0. So a3, which is the first ancestor of 3, so that is 2. Okay, so 2 is the first ancestor of 3. And what's the first ancestor of 2? So first ancestor of 2 is 1. Okay, so it results in 1. And similarly all gonna result in 1 because every other ancestor is 1. And after that 4 gonna call, after calling 1, 3, 4 from 2, I mean now 3 gonna call for 2 and 5, but 2 is his parent, so it's gonna call for 5. Okay, so for 5 we gonna call for 5. 5 whose parent is 3 and depth is 3. 5 whose parent is, whose depth is 3 and parent is 3. Okay, so now calculate the 0 to the power, I mean second ancestor of 5. Okay, so what is the second ancestor of 5? The second ancestor of 5 is a to the power, I mean a5 0 0. And what is the first ancestor of 5? First ancestor of 5 is 3. If we see first ancestor of 5 is 3, and what is the first ancestor of 3? If we see first ancestor of 3 is 2. Here, first ancestor of 3 is 2. So it gonna result in 2. Okay, so it gonna result in 2, and the rest of all gonna result in 1. If you calculate the fourth ancestor of E, so if you calculate the A5, I mean fourth ancestor of 5, that is 2 to the power 2. So it gonna result in A first and second ancestor, I mean 1. So A, which is the second ancestor of 5? So second ancestor of 5 is 2. Now what's second ancestor of 2? So second ancestor of 2 is second ancestor of 2 is 1. Okay, is it second? Yeah, it is second. Second ancestor of 2 is 1. So what it will also gonna become 1. The fourth ancestor of, I mean 2 to the power 2th ancestor of 5. And after that, for now we have to calculate for g. I mean g. So for 4 we calculated 2, for 1 and 7, and now for 6, for 5 we calculate for 3, and now for 6 we have to calculate for 1 and 7. So for 6 gonna calculate to 7 whose parent is 6 and depth is 2. Okay, so depth whose parent is 6 and 7 whose parent is 6 and depth is 2. And now find the second ancestor of 7. So that is for 7 find the second ancestor, that gonna become ancestor of first ancestor, I mean first ancestor of first ancestor of 7. Okay, so that's gonna become, what is the first ancestor of 7? So first ancestor of 7 is 6, and now we need the first ancestor of 6. So what is the first ancestor of 6? For 6 it's 1. Okay, so it's gonna represent 1. So second ancestor of 7 gonna be 1, and the rest of all gonna become 1. Similarly, recursively. So finally we got the total, I mean ancestor matrix, the depth array, and now we can calculate the lowest common ancestor. So after doing this on simple DFS code, that may look scary, but the code is barely of 5 lines. So after doing the DFS, we are going to call the LCS, I mean lowest common ancestor of 2 nodes. Okay, so for example, we are going to calculate the lowest common ancestor for 7 and 3 because they are at same level, and how we are going to take them at same level we are going to discuss it later. Okay, so we are going to, because their difference between depth is 0, so for 6 and 7 what we are going to do is just a little partition. So for 6 and 7 we have to call the LCS. Okay, and what was the LCS, lowest common ancestor? How we are going to find the lowest common ancestor is, we are, so let me write the little code. LCS, hold on, for j equal to 18. Yeah, we started, so we only need 17 because 0 is also an ancestor. So j equal to 17, j greater than equal to 0, and j minus minus. We are going to start from root and look the common ancestor from here. We are going to start from 1 and look for the common ancestor. We have, if we have more nodes and here is the root, we are to going from start from root and look for the common ancestor, and when we find difference we are going to lift it up until we reach the common ancestor. Okay, so let me show you. And here just a simple code. If ancestor, I am writing ancestor as a ancestor of jth ancestor of u is not equal to vth ancestor of j, what we are going to do, we are just going to uplift it. Okay, until the mid, I mean we are going to uplift it u equal to ancestor of, we are going to uplift u by jth time and uplift v by jth time. Okay, ancestor v, jth ancestor of v, and this is the LCS u and v. So I'm considering u or v at same level, u and v are at same level. Okay, so how we are going to find the common ancestor, and at last we are going to return the first ancestor of u. Okay, so why this works is, so for example we are at 3 and 7. Okay, so we started from j equal to 17 until we find an ancestor which is not common. Okay, so 2 to the power 17 ancestor is common, 2 to the power 16 ancestor is common both in 7 and 3, and in 7 and 3 we found a 7 and 3. Here we go. B. At the first ancestor, we found the first ancestor were not common because this fourth ancestor were common, and here we found the first ancestor which is not common. Okay, so the value of j is 0 here. Okay, so that was the last, I mean last loop where j greater than, after that j minus 1, j gonna become minus 1. So we found that the j equal to 0, at j equal to 0 they both are not equal. So we are going to do, I mean 3. Okay, here initially u equal to 3, and now u gonna become u equal to ancestor of, yeah, what initially u is 3. So g is 0. So the first ancestor of 3. What is the first ancestor of 3? That is 2. Okay. So we got first ancestor of 3 is 2. So u become 2 and v is 7. So what is the first ancestor of 7? I mean jth ancestor of 7, because j is 0 here. So jth ancestor of 7 also gonna become 6. Okay. If you see here, jth ancestor of 7 gonna become 6. So at last, and this is the last loop, so we got this as output. And after that, what we are going to do is, I mean, what we are going to do is, after exit the loop, and we're going to return the first ancestor of u. And what is u equal to 2, and first ancestor of 2 is 1, so we are going to return 1 as LCA. So here we got the lowest common ancestor at 1. Okay, so let me show you example in a big tree. Okay, so for example we have something like first node, second node, third node, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay. So basically, let's consider we are at this node. Okay. Okay. So if we starting from here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. This is the last node, so it's equal to 70. And at j equal to 70, the common ancestor were same. Okay, and j equal to 16, the common ancestor were same at 15, 14, 13, 12, 10, 11, and what is this? This is 10. Till 10th ancestor, the common node was same. Okay, but as we decrease to 9th ancestor, what we are going to, this is the 1, I mean this is first ancestor, second, third, fourth, fifth, I mean let's consider it sixth. So this is first ancestor, this is second, this is third, this is fourth, this is fifth, this is sixth. So till sixth. Okay, so if we at 7, we at 7th we got the common ancestor, but at j equal to 6, I mean at here we got at j equal to, here, here maybe many nodes. Here j equal to, it's j equal to 0, j equal to 1, it's represent j equal to 2, it's represent j equal to 3. Here 8 represents j equal to 3. So at j equal to 3 we have common node 8. At j equal to 4 we are going to, I mean we are going to end up at 4. We found this node is not common, so what we are going to do is we are going to find the fourth node of, I mean we are going to lift it by fourth. Okay, here for example here we are u, here we are v. So at fourth we found the fourth ancestor isn't common, so we are going to lift it to fourth ancestor. We are going to making the u to its fourth ancestor. Okay, so this gonna become u. now the current u and u. So that this is the u, new u and new v. This is gonna become new a and new b, and we found at j equal to 2. Okay, j equal to 2, and now at j equal to 1, we are at the first ancestor. Is first ancestor in common in both? Is first ancestor is common? Okay, so first ancestor is not common, so we are going to lift it to the first. Okay, I mean j equal to 1, I mean second ancestor. So second ancestor of u dash is 6, second ancestor of v dash is 6, but 6 is not common. Okay, so we are again going to lift it till there. So this is u double dash, this is u dash, this is v double dash, 6 is v double dash. Okay, so after that we are j equal to 0. So is j of, I mean, zeroth first ancestor of u and v is common? Yes, it is common. So we are going to return the, if it's gone, it's have to be common. Okay, it can't, it cannot be not common. I mean, it cannot become to one. Okay, if it reaches one more, so at starting we are going to exceed this. Okay, so that's why this works. We are going to return the first ancestor of u double dash, so that is 7. So at the end we got the least common ancestor. Okay, so that's how we are going to get the least common ancestor. And how we are going to make u and v at same level? So we are going to insert a piece of code here, that is first, I mean, writing the code here. If depth of u is less than depth of v, if depth of u is less than depth of v, we are going to swap u and v. Swap u and v. Here we are considering u is greater than v. Okay, greater than v. This we did this to make all, to make sure that u always remain greater than v. Okay, I mean depth of u always remain greater than v, and we can get difference is positive. Okay, so difference equal to depth of u minus depth of v, because here depth of u is more, so we are going to uplift the u till v to make it on same level, because our LCS code only gonna work if both are on same level. Okay, so what we are going to do is for int I equal to uh, or j equal to 0 and j less than 17 and j plus plus, we are going to do if jth bit is set in difference, we are going to uplift it by j. Okay, so I'm going to do a dry run. If jth bit of difference is set, we are going to u equal to ancestor of u j times. So what this basically means is, so this is inside this and this is inside this. So from j equal to 17, what we are going to do is, for example, we got a difference. So here 1, 2, 3, 4, 5, 1. Okay, so we got difference here. So here depth for A, for B, here depth is 1, I mean depth equal to 1. Here depth equal 1, 2, 3, 4, 5. Here depth equal to 5. Okay, so the difference equal to 4. So what's 4 in binary? So the 4 in binary gonna become 0, 0 and 1, 0, 0. Okay, so 2 to the power 0, 2 to the power 1, 2 to the power 2. Okay, so it's gonna represent 4. So is 17 bit is set here? Yes, I mean it is 0 bit is set. It isn't, so we're gonna skip this. Is first bit is set? Now is second bit is set? Yes, if second bit is set, here what we are going to do, we are going to uplift it by second. Okay, and here j2 means we are going to uplift it by, so u is going to become ancestor of u, and j is here second bit is isn't, I mean second bit is set, so we are going to uplift it by second to where j equal to 2. Okay, and uplifting it by second means if we do the uplift by second here, uplift by second means lifting it to 4 node. Okay, so uplifting it by second means uplifting it to 4 node, so here d gonna become 1, 2, 3, 4. So it's gonna become new a dash. Okay. So these gonna become new a dash or okay u dash. You can call it. Okay. And it can work on any number. If we get difference equal to 19, so binary of 19 gonna become, I mean 16 plus 17, 18 plus 1. Okay. So this gonna represent 0. I mean 1, 1, 0, 0, 1. I mean 1, 2, 4, 8, 16. So this is binary. So we first uplift it by 16, then uplift it by 2, and then uplift it by 1. And a cool thing here, because we are storing it in power of 2, and the set bit it also doing it in power of 2 because the number in computer memory is stored in binary. So that's why we used the power of 2 here. Okay, to make this. And so there are many other factors to using second power, so that's why this code one. Okay, so this is the total LCS code, I mean this and this is the total LCS code, and the DFS code is with this one. Hold on, this one is total DFS code, and that's the try run we did. Okay, I mean it may seem too messy. If you give it a go 2-3 times, it all gonna make sense. So let's code it and see how much we got it. So let's open the editor. For now, let's remove that. Okay, now let's vector vector in adjacent. Let's first define the adjacent, then define the vector, the depth array to store the depth of every, and define the vector that containing array of integer data type of size 18 and call it ancestor. We are calling it ANC. Okay, to save us some time. And after that, let's write the DFS code. So it's gonna take node as parameter, another parameter is parent, and another is the current depth. Okay, let's call it D. So first dpt depth. So depth of current node is current depth, that is D, and after that we are setting the ancestor of current node, and first ancestor of current node, that is parent. Okay, so the first ancestor of current node gonna become parent, and for n j equal to 0, we've set the first ancestor, so we are going to 2 to the power, we set the 2 to the power 0th ancestor, so we are going to set the 2 to the power 1 till 2 to the power 18th ancestor. Okay, so 2 less than 18, I mean 2 to the power 17, and j less than 18, j less than 18, and j plus plus. And how we are going to do, we are going to that use that recursive relation we got, and I don't know why I'm using ANC of current node of jth ancestor equal to ancestor of current node of jth minus 1's ancestor and j minus 1. Okay, I think everything is right there. And for every child and ancestor, I mean adjacent, we are, if it's not equal to parent, if child isn't equal to parent, we are going to call the DFS there, DFS on that child. Current node gonna become child, current node gonna become child, and child gonna become current node, and current node gonna become parent, and increase depth by one. Okay, so we called the DFS there. So that's all the DFS, and now let's come to LCS, how to find the lowest common ancestor, LCA. Okay, so for LCA, it's gonna represent the integer. We take 2, we are going to represent the lowest common, I mean we are going to calculate the distance between lowest common ancestor of u and v between two nodes. So first let's take the, if depth of u is less than depth of v, we are simply going to swap u and v. We are simply going to swap u and v and calculate the difference. Depth of u minus depth of v. We are just taking care that u always gonna have, u is always stay in more depth. And now for int j equal to v, now we are uplifting the u, I mean to the same level as v, j less than 18, j plus plus, and checking which bit is set in diff. If jth bit is set in diff, what we are going to do is, and 1, if jth bit is set in diff, what we are going to do is we are going to uplift it ancestor to its ancestor to jth time, I mean 2 to the power j, because in binary it also gonna represent the j. So it's the ancestor of u j. Okay, so after uplifting it, the next thing is, if little optimization, if u equal to v, if u are v, u and v gonna become same, I mean if they lies on same path, u and v gonna become same, so we gonna simply return the u. Okay, so after that, for and j equal to 17, j greater than equal to 0, here we are traversing from root node, so here we are, I mean traversing the our ancestor matrix from right to left, okay, in reverse manner. And if until then we found our ancestor u with ancestor jth ancestor of, if jth ancestor of u is not equal to jth ancestor of v, we are simply going to uplift both. Okay, u equal to jth ancestor of u by j, I mean 2 to the power j time, equal to ancestor of v times j. Okay, till then, and at last we are going to return the first ancestor of u. At last we are going to return the first ancestor of u, and after that, just hold on. Now let's initialize the answer here. Vector integer answer of size queries dot size, and now let's create the adjacent array for every query and queries. What we are going to do is, int u equal to q0 and v equal to q1. Now let's connect q and v by pushing adjacent of u dot push back v, and then push back u and adjacent of v, and that's how we are going to create the adjacent list. And after that, what we are going to do is, oh, hold on, I think I messed up. It's gonna become edges. We have to first connect the edges, and now then we are going to move the query for and query uh, FCQ on queries. What we are going to do is int u equal to first node of query, int u equal to second node of query, and after that, if u equal to v, if both are same node, we are simply going to answer dot push back. If both are same node, we are going to answer dot push back 0, because there are actually no ways to select. I mean, no ways to select, but assign the weights to the edges. And now calculate the lowest common ancestor between u and v. So lowest common ancestor is, let's pass u and v, u comma v. So this one represent the lowest common ancestor. And what is our formula to return the, I mean, to get the number of edges? So it's, you know, and number of edges between both. So let's call it k. So that gonna become, okay, I can write it, number of AD edges, AD edges between u and v. Okay, so number of edges between u and v equal to depth of u plus depth of v minus twice of depth of lowest common ancestor over. So that's the number of edges between u and v. And we are simply going to answer dot pushback, answer dot pushback, I mean, simple function here, power of 2 k minus 1. So I mean, this is simply power of 2. I mean, 2 to the power k minus 1. We are going to simply put 2 to the power k minus 1, and we can make the function here. In function, we can calculate the every power, every possible powers. So how we are going to do is, first vector of long type, let's call it power of 2, and size is, its size is edges dot size. Hold on, and n equal to AD edges dot size. So the number of node is edges dot size plus 1. That is number of node. Okay, we have to resize the adjacent. I forgot to resize the dot resize. So resize it n plus 1, and let resize the depth also. Depth dot resize n plus 1. We are leaving 1 for 0 index. Resize the ancestor array, I mean ancestor matrix, to n plus 1. And now power of 2 to n plus 1, power of 2 to n plus 1. And yeah, basically it is a vector of that gonna contain where first index gonna contain 0 to 2 to the power 0, second gonna or second index gonna contain 2 to the power 1, third index gonna contain, I mean 2 index gonna contain 2 to the power 2, 8 index gonna contain 2 to the power 8. And how we are going to do that is for and I equal to 1, I less than equal to n, I plus plus, what we are going to do is power of 2 and I power of 2 equal to I minus 1 power of 2 times 2. Okay. I minus 1 power of 2 times 2 times 2 and do we can do a modulo to mod, and let's define a mod. Long 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 mode, and also we can have int. Int can have that 1 e 10 to the power 9 plus 7. Okay. We forgot to return answer. Return answer. Yeah. What we forgot, and the word int. Okay. We forgot to add the name there. Okay, after doing some cleanup, I think our code had successfully run. I think what I did is basically here we forgot to pass the node in adjacent, and now see there was some structure issue, and then and here I called the DFS after making the edges, after making the adjacent. Okay, after that, what we did is we calculated the power of 2. We for every query calculate the LCA, and we use the formula that we derived, and instead of push back we did a minus 1 and divide by 2 to make sure only odd one get pushed. And I think basically that's all I did. And we calculated, here is the code of LCA how to calculate. This one is code, this one is to uplift you to same level as we had swap. I think we did swap to pure Q is deepest. Make sure Q is deepest. We did this play Q B until both common system. So that's all. We want to recite everything using ADG for the DFS. DFS calculate power to in like 1 power to. After that, we for every query we did this the formula in formula. After all this, I think that's all we did. We can see DFS, and if we submit the code, let's submit the code and see if it works or not. Okay, so we got a perfectly fine code here, and mm, I think the time complexity here is total number of queries, and to log n, if we remove the times to into log n, log or number of edges, so time complexity here become equal to big O of one half in log of number of edges one half in the edges times width. Okay, one of queries and the same also equal to space complexity. Okay, and after that, okay, so I hope you like this video. So please make sure you practice it one or two times. I mean, what we did here is binary uplifting. You can call it DP on tree because the ancestor matrix was a kind of DP. We are pre-computing the sub parts, I mean sub problem to solve a big problem. So DP on tree, and also another concept of lowest common ancestor. Okay, lowest common ancestor, how we uplift lower common ancestor by 2. Okay, so these are the concept. You can study it separately from a chat or in YouTube, and think and give it a try. So I think that's it for today. Make sure to subscribe to Tensor, and if you like our video, so please leave a like. That means a lot for us, and feel free to ask any doubts if you have in comments or any mistake if I did while explaining things. And till then, keep smiling, keep coding.